Hey everyone, and welcome back for another deep dive. Today we're going to be talking about something that sounds pretty sci-fi. Cold welding.
Oh, yeah.
It's where metals just fuse together without any heat involved.
Right.
And we're diving into this topic because, you were really interested in the cocktail party chemistry episode about it. So we thought we'd take a closer look.
Absolutely.
What really grabbed your attention were these 5 intriguing factoids about cold welding, and we're excited to unpack those with you today.
Yeah, for sure.
So just to quickly recap,
Yeah.
the 5 things that really piqued your interest were that metals can bond without heat,
Okay.
and then it's a problem in space.
Mm-hmm.
It's also used in nanotechnology.
Right.
It has something to do with atomic structure and oxidation.
Interesting.
And get this, it was discovered by accident during some early vacuum studies.
Wow, that's wild.
So where do we even begin with all that?
Well, I think the best place to start is to really understand what's happening at the atomic level when we talk about cold welding.
Okay, so walk me through this.
Sure.
How do metals just magically fuse without any heat?
Well, it might seem like magic, but it's really not.
Okay.
Picture 2 pieces of metal that are polished to an almost mirror-like finish.
All right, I'm picturing it.
And now imagine zooming in with like a super-powered microscope.
Okay.
Even on those seemingly smooth surfaces, you'd see these tiny bumps and irregularities at the atomic level.
Oh, really?
Yeah, they're called asperities.
Asperities.
Asperities, yeah.
Okay.
When those asperities come into contact with enough force,
Okay.
and this is important, the surfaces have to be really, really clean with no oxide layers getting in the way.
Uh-huh.
The atoms on those surfaces can actually bond.
Wait, so you're saying the atoms from one piece of metal just latch onto the atoms of the other piece just like that?
Exactly. The electrons in their outer shells start to overlap,
Okay.
and you have a metallic bond.
Uh,
And remember, this is all happening without any heat.
right.
So it's not like melting 2 pieces together with a torch or anything.
Okay.
It's more like they become, on an atomic level, just one unified piece.
That's pretty incredible.
It is.
It really challenges like how we think of metals working.
Yeah.
So if it's all about clean surfaces, what role does this no oxidation thing play?
That's key.
Okay.
See, most metals, when they're exposed to air, they form a thin layer of oxide on their surface.
Mm.
It's like a protective barrier.
Okay.
And that oxide layer prevents the atoms from getting close enough to form those metallic bonds.
So the oxide layer is like a metal bodyguard,
Uh-huh. Yeah, you could say that.
keeping those atoms from getting too friendly.
Exactly. And it's only when those oxide layers are absent, either through like special prep in a controlled environment or in the vacuum of space where there's no oxygen to cause oxidation,
Right.
that the atoms can get close enough to bond.
Okay, that makes sense.
Yeah.
So that directly connects back to the factoid about atomic structure.
Mm-hmm.
No oxidation means those metal atoms are ready to mingle.
They are.
Now let's switch gears and talk about the space problem. This whole idea of unplanned sticking of components in space,
Yeah.
that's got to be a headache for engineers, right?
Absolutely. In the vacuum of space, you have the perfect recipe for cold welding.
Oh, how so?
No air means no oxide layers to protect the surfaces.
Right.
So any 2 metal components that come into contact under pressure
Mm-hmm.
have a very high chance of cold welding together.
And that can't be good.
No, not at all. Imagine a crucial piece of equipment on a satellite suddenly fusing shut because of this.
Mm.
Not a scenario you want millions of miles from Earth.
Definitely not.
Ugh.
Are there any real-world examples of this happening?
There are actually. One that comes to mind involved the Galileo spacecraft.
Okay.
It had this high-gain antenna,
Yeah.
a super important part of its communication system,
Right.
and it was designed to unfold like a giant umbrella once it got to Jupiter.
Whoa, that's cool.
Yeah, but when they tried to deploy the antenna in space,
Yeah.
some of its ribs had cold welded together during storage.
Oh, no.
They were stuck.
So like a giant metal umbrella that refused to open.
Basically.
What a nightmare.
It was a big setback for the mission.
Wow.
And it highlighted how serious an issue this can be in space.
For sure. It's amazing to think that something we might not even think about as a problem on Earth can have these consequences in space.
I know, it's crazy, right?
It really shows how important careful planning and engineering are when it comes to space.
Absolutely.
But let's move on from potential disasters and talk about how cold welding is being used in nanotechnology.
Okay.
This one really stood out to me because it seems like the opposite of the space problem.
It's pretty fascinating how this phenomenon that can cause so much havoc on a large scale can be used for such precise and delicate work at the molecular level.
Exactly.
Yeah.
So how does cold welding even work in nanotechnology?
Well, imagine you're trying to build a machine the size of a virus.
Okay.
You can't exactly use a blowtorch.
Right.
That's where cold welding comes in.
I see.
Researchers have these incredible techniques to manipulate individual molecules and bring them together with enough precision to trigger cold welding at that point of contact.
So they're like playing atomic Legos,
Yeah, basically.
building these structures one molecule at a time.
That's a great way to think about it. And the beauty of cold welding in this context is the control it offers.
Okay.
You can join these tiny components without introducing any heat,
Right.
which would be a disaster for delicate structures at that scale.
Yeah, for sure.
It's not just about the size, it's about avoiding heat damage.
It's amazing. I'm starting to see why this factoid about molecular scale bonding caught your attention.
Mm-hmm.
What are some of the potential uses for cold welding in nanotechnology?
The possibilities are huge. One area is creating nanoscale sensors.
Oh, cool.
These tiny devices could revolutionize everything from medical diagnostics to environmental monitoring.
Give me an example.
Okay, so imagine a sensor so small it could detect individual cancer cells in the bloodstream.
That would be amazing.
Right. Early detection is key.
Yeah. Are there any other uses besides sensors?
Yeah, another exciting area is molecular machines.
Molecular machines?
Yeah, these are tiny, intricate devices built from molecules,
Okay.
and they're designed to do specific tasks at the nanoscale.
So like tiny robots.
Exactly, like tiny robots working at a level we can barely even comprehend.
Wow.
And cold welding plays a crucial role in assembling these machines.
This is blowing my mind. We've gone from potential space disasters to building tiny machines with cold welding.
Yeah,
It's so versatile.
it is.
Okay, I need a minute to process all of this.
Take your time.
This deep dive is already exceeding my expectations.
Just wait till we get to the story of how cold welding was discovered.
Oh, I love a good origin story.
Yeah.
Let's hear it.
So picture this. It's the early 20th century, and scientists are just starting to explore this strange world of vacuums.
Okay.
Building these elaborate contraptions to remove air from chambers and observe how materials behave in this unfamiliar environment.
Like they're creating tiny artificial slices of outer space right here on Earth.
Exactly. They were pioneers in a way, pushing the boundaries of what we knew about the physical world. And one of these intrepid explorers was a scientist named Thomas Preston.
Oh.
He was really interested in the properties of metals in a vacuum.
So it was during one of his experiments that he stumbles upon this whole cold welding thing.
That's right, a remarkable accident.
It really highlights how progress often involves meticulous planning and a bit of luck.
Absolutely. Now, Preston wasn't setting out to discover cold welding.
Right.
He was studying the behavior of metal surfaces in a vacuum, meticulously polishing them and placing them in his vacuum chamber.
So what was it that led him to this groundbreaking observation?
Well, after leaving the metal samples in the vacuum chamber for a while, I came back to examine them and noticed something really peculiar.
What was it?
Some of the metal pieces had adhered to each other.
Wait, so there was no heat involved at all?
Nope, none at all.
How is that even possible?
That's what baffled Preston at the time. He documented his observations, carefully repeated the experiment, and ruled out any other explanations.
So it was a true eureka moment.
It was.
When he realized he'd stumbled upon something that challenged everything they thought they knew about metal.
Exactly. It makes you wonder how many other scientific breakthroughs have happened because of these kinds of unexpected observations.
For sure. It's a testament to the importance of curiosity and a keen eye.
I agree. Now, as you might imagine, Preston's discovery wasn't immediately embraced by the entire scientific community.
Right, because it challenged a long-held belief.
Precisely. There was pushback debate, further experimentation.
It's not every day that a fundamental concept in science gets turned on its head.
That's true. But as more scientists replicated Preston's findings and dug deeper into the atomic mechanisms at play, the evidence became pretty undeniable.
And that's how cold welding transitioned from a curious anomaly to a recognized scientific phenomenon.
Exactly. It's a process of constant refinement and exploration. And over the years, our understanding of cold welding has only grown more sophisticated, leading to those applications in space exploration and nanotechnology that we talked about.
It's quite a journey for something that began as an unexpected observation in a vacuum chamber.
It really is. So we've explored the physics of cold welding, its implications for space travel, and its potential to revolutionize fields like nanotechnology.
Right.
What stands out to you as the most remarkable aspect of all of this?
Honestly, for me, it's the incredible versatility of cold welding.
Oh, yeah.
On the one hand, it can pose a significant challenge in space,
Mm-hmm.
where unplanned bonding can jeopardize missions.
Right.
But on the other hand, it can be harnessed as a precise tool to build intricate structures at the molecular level.
I agree. It really speaks to the power of understanding the fundamentals of science.
I'm with you on that.
Mm.
It's a fantastic example of how something that's seen as a problem in one situation can be a solution in another. And it all boils down to understanding how atoms behave and the conditions that allow them to bond without heat.
It does. But before we wrap up, I'm curious, did anything about our deep dive surprise you?
Honestly, the sheer range of applications surprised me the most.
Yeah.
The fact that we can go from discussing the challenges of cold welding and the vastness of space to its potential in the tiny world of nanotechnology is incredible.
I know, it's amazing. And of course, the story of its accidental discovery is a great reminder that scientific progress often hinges on serendipity and a keen eye for the unexpected.
You're absolutely right. Those unplanned moments in science can often lead to the most fascinating paths of exploration.
Yeah, for sure. And it makes you wonder, what other hidden potential does cold welding hold?
Yeah.
What if we could use cold welding to create self-healing materials?
Okay.
Imagine materials that could repair themselves at the molecular level,
Wow.
mending cracks or damage without any intervention.
Now, that would be revolutionary.
It would! Think of the implications for infrastructure, electronics, even medical implants.
Right. If we could design materials that could basically stitch themselves back together.
Exactly. It could drastically increase longevity and reduce waste.
It's a pretty amazing concept, but surely there must be challenges involved in making this a reality.
Of course. It's a complex area of research. Controlling cold welding at such a fine level and ensuring these materials are reliable and safe, it'll require some big advancements, but the potential benefits are huge.
They are.
And it's these kinds of what-if questions that really push scientific innovation forward.
You've given me a lot to think about. This deep dive has been eye-opening.
Good. I'm glad.
I had no idea that cold welding could have such wide-reaching implications.
It's amazing, isn't it? It's a testament to the interconnectedness of science and the power of curiosity. Even a phenomenon that might seem like a mere curiosity can unlock so much.
And to our listener, we hope this deep dive has sparked your own curiosity about cold welding.
I hope so.
From those accidental discoveries to space exploration to nanotechnology breakthroughs, it's a field that continues to surprise and inspire.
Absolutely. And who knows what amazing applications we'll discover in the future.
Yeah, it really makes you think, doesn't it?
It does.
Like, what other hidden wonders are out there just waiting to be discovered?
Exactly. And speaking of discoveries, I think we should revisit the story of how cold welding was actually observed for the first time,
Oh, yeah, you're right.
because it really highlights the role of serendipity and a keen eye for the unexpected in scientific progress.
You're right. We talked about Thomas Preston's accidental discovery a little earlier.
Yeah.
But I'd love to dig a bit deeper into like the specific circumstances that led to that pivotal moment.
Of course. So remember we were talking about how scientists in the early 20th century were kind of obsessed with vacuums.
Right.
They were building these really elaborate contraptions to remove air from chambers and basically create these mini artificial environments that had no atmospheric gases.
Yeah.
These early vacuum chambers were like windows into a whole new realm of physics.
It must have been such an exciting time to be a scientist.
Oh, absolutely. Every experiment was a journey into the unknown. And Thomas Preston was one of those explorers venturing into this uncharted territory.
Yeah.
He was especially interested in how metals behaved in a vacuum.
Interesting.
Like, how would their structure change? How would they interact with other materials in this alien environment?
So he was really pushing the boundaries of what we knew about metals.
He was a true pioneer,
Yeah.
and it was this spirit of inquiry that led him to stumble upon cold welding. So picture Preston in his lab, meticulously polishing these metal samples and carefully placing them inside his vacuum chamber.
Okay, I'm picturing it.
He was a stickler for precision.
Yeah.
He wanted to make sure his experiments were super pure.
I can imagine him like adjusting the vacuum pressure,
Oh, yeah.
double checking his gauges,
Mm-hmm.
patiently waiting to see what would happen. It's really a testament to the patience and dedication that's required in scientific research.
It is.
It
And
is.
when he came back to look at the samples, he noticed something strange.
What was it?
Some of the metal pieces were stuck together.
But there was no heat involved.
Right.
None whatsoever.
No melting or anything.
Nope. And that's what made this so bizarre.
It really is strange.
At first, he probably thought it was a mistake.
Right.
Like maybe something had contaminated the samples or
Right.
there was a problem with his setup.
That makes sense.
But something told him to investigate further?
Like his scientific intuition was tingling?
Haha, yeah,
Or
maybe. So he very carefully documented everything he saw,
Oh.
repeated the experiment,
Mm-hmm.
and ruled out any other possible explanation.
Wow.
And then it hit him. The metals were bonding in a vacuum without any heat.
Which was unheard of at the time.
Totally unheard of. It was a huge moment in the history of material science.
It must have been.
And while his discovery was initially met with some doubt, it eventually led to a whole new understanding of atomic bonding.
It's amazing how scientific progress often comes from these unexpected places.
It is. It's the things that don't fit the mold.
That lead to the biggest breakthroughs. And as we wrap up our deep dive into the world of cold welding, I think it's important to remember to keep your mind open to the unexpected.
That's good advice.
The world of science is full of mysteries just waiting to be uncovered. And sometimes the most profound insights come from the most serendipitous moments.
It's been great exploring this topic with you, and I hope our listeners found this deep dive into cold welding as enlightening as I have. Remember, curiosity is key to unlocking new knowledge. So keep asking questions, keep exploring, and never underestimate the power of an accidental discovery.